In this video, we'll be tackling the topic 5.2, which has to do with Hess cycles. Please note that this is an essay chapter, therefore all students are required to work on it. The content I will cover in this video is as follows. What is the Hess law, how to draw Hess cycles, and the calculations involved in Hess cycles, including the enthalpy of reaction and the enthalpy of formation. Before tackling this topic, it's important that you familiarize yourself with the notion of enthalpy and energy changes, which is discussed in section 5.1. A chemical reaction happens in numerous steps. You may already be familiar with the concept of reaction mechanisms if you've covered the chapter on kinetics and mechanisms in organic chemistry. Think of the medieval saying, all roads lead to Rome. Well, the same thing applies to chemical reactions, as shown on the diagram on the right. A reaction can take different paths, but still create the same product. In this case, both routes lead to the formation of a cholesterol molecule. Keeping this medieval saying in mind, the Hess law states that the enthalpy change for any chemical reaction is independent of the route, provided that the starting and final conditions of the reactants and products are the same. So, for instance, in this chemical pathway, in those chemical pathways, whether you take the black pathway, so this route, or you take the blue pathway, so this route, each of the pathways will lead to the same energy change. This is basically what the Hess law is all about. So to put it in a simpler context, if we have a generic equation, A plus B changes to C plus D, and let's say that the energy change for this reaction, going like that, energy change is equal to X. And X would also be equal to the sum of any pathway taken by this reaction. So for example, if the reaction goes by intermediate products, the sum of the energy change from this point to that point and from here to here would be equal to X. So therefore, Y plus Z will always be equal to X. Another way of seeing that is that the sum of all clockwise reaction, so from here to here, we're going clockwise, is equal to the sum of all anti-clockwise reaction. So if we're going from here to here to here, this is an anti-clockwise reaction. Therefore, the sum of the clockwise reaction is equal to the sum of the anti-clockwise reaction. With all of this in mind, how do we draw a traditional Hess cycle? Well, we first need to write down the equation, which is done for us here. So CH4, which is methane, plus 2 moles of oxygen changes into carbon dioxide plus 2 moles of water. Then we need to consider the formation of each reactant and each product from all the separate elements considered in the reaction. This is done like so. So if we have all the elements present in this chemical reaction written down here, so for example we have carbon plus hydrogen, so plus oxygen in their standard form. So we need to consider the formation of the reactants and the formation of the products. So basically, what type of enthalpies are we dealing with here? The enthalpy change of reaction, of course, so delta HR is from the reactants to the products, but we are also dealing with the enthalpy change of formation of the reactants and the enthalpy change of formation of the products. So in this case, products, and here reactants. Okay, just a little recap for you. What is the enthalpy change of formation? The enthalpy change of formation is the change in enthalpy when 1 mole of a substance in its standard state is formed from its pure elements under the same conditions. So, for example, if I were to write the equation for the enthalpy change of formation of magnesium oxide, so I'd start with magnesium, which is a solid at standard state condition, plus oxygen, which is a gas at standard state condition, changes into magnesium oxide, which is a solid, I believe, at standard state condition. And the definition of enthalpy change of formation clearly states that we need to form 1 mole of the substance. So when we balance the equation, we need to keep this in mind, that this coefficient always has to be 1. Therefore, we simply divide this by 2. We add a half in front of the oxygen in order to form 1 mole of magnesium oxide. So that was just a recap on what is the enthalpy change of formation. So now if we want to put all of this together, how do we calculate the enthalpy change of reaction using a Hess cycle? So we are going to use the enthalpy change of formation of the products. So it's going to be the sum of the enthalpy change of formation of reactants. And here we're going to use the sum of the enthalpy changes of formation of the products. Fortunately for us, the enthalpy changes, or the enthalpy change of formation of common compounds, are listed in the data booklet, section 12 of the data booklet. So we can use the data provided to us in order to determine the enthalpy change of reaction for the combustion of methane. Let's go about and do that. So the enthalpy change of formation for methane is equal to minus 74 kilojoule per mole. So that is delta HF4CH4. Okay, is equal to that. And one thing that we need to keep in mind is that the enthalpy change of formation of any element, for example oxygen, is equal to 0. So we only care about the enthalpy change of formation of methane. Now let's take a look at the product side. We need the enthalpy change of formation of carbon dioxide plus 2. So we have 2 moles of water, and we know that as per the definition, the enthalpy change of formation for any compound is going to be for 1 mole. Therefore, we would have to multiply the enthalpy change of water, or in this case steam, because there's a different value for the enthalpy change of water in the liquid state and in the gaseous state. So in this case, I would consider the enthalpy change of formation of steam. So I'm going to have to multiply this value by 2. So delta H of formation of H2O gas, in other words, steam. This is going to give us an answer. So the standard enthalpy change of formation of carbon dioxide is minus 393.5 kilojoule per mole, plus 2 times the enthalpy change of formation of water or steam is equal to minus 241.8 kilojoule per mole. Alright, and what we want to do now is we want to use all those values in order to determine the enthalpy change of this reaction right here. And this is the tricky part. We need to know what to add with what and what to subtract, or how do we obtain a value. Right, so we are going from here, so that's the starting point, to here, and that's the end point. And according to Hess law, clockwise is equal to anti-clockwise, the sum of the energies from here to here should be the same as anti-clockwise. So from here to here. That's a bit messy. Apologies for that. So really what I'm going to do is that I'm going to add the values that I have, but I need to be careful with the directions and the sign. What do I mean by that? So the first step is going from, let me just change color here, going from here, so that's the starting point, to here. Okay, so that's the first step. And we have a value for the enthalpy change of formation of the reactants, but that's really going from the elements to the product, which is here. And the value for that is minus 74. But we are doing the opposite right here. Therefore, the sign will switch. So the first value would be from here to here would be minus 74, which is obviously positive 74 kilojoule per mole. Right, so now the second step is going from here to the final product. And in this case, we have this here, which you can just plug into your calculator. And in this case, we do not have to change any signs because we are going in the same direction. So I'm just gonna do the working here. So it will be minus 393.5 kilojoule per mole and plus 2 times minus 241.8 kilojoule per mole. And this is something that you can easily plug into a scientific calculator, which you should have in your chemistry exams. And if you plug all of that, you get minus 803.1 kilojoule per mole. So this is the final answer, and it is the enthalpy change of this reaction right here. Okay, so the things to remember, the stupid mistakes that many students can make. First of all, remember to look at the signs and the direction. So in this case, for example, if you need to change direction, you need to change the signs. So remember that. And the second thing that you need to always be careful to is if you need to multiply anything by the coefficient. So for example, here in the product side, we've had to multiply the enthalpy change of formation of water by 2 because we had a 2 in the reaction.